Hello everyone. Today I am going to start a new topic, that is Introduction to Kinetic Theory of Gases. Okay, so here KTG means Kinetic Theory of Gases. Okay, so we know that a matter a matter is made up of atoms, correct? A small indivisible atoms. So we know that matter is made up of atoms. A few atoms bind together to form a molecule, right? A few atoms bind together to form a molecule. A molecule is a smallest unit that can exist in a free state and possesses all the basic property of a substance as concerned. So if I have a substance, so all the basic property of this substance is the result of the atoms coming close together and forming a solid. A molecule can move continuously, and this motion becomes more and more chaotic when there is thermal excitation. So if the atoms are very close together, then it will form something called as solid, correct? So if the distance between the atoms increases, then it might turn into a liquid. Okay, if further it is increased, then it is converted into a gas, correct? So why this happens? So here, if you try to increase the thermal excitation between the atoms, so what happens is there will be more chaotic motions among the molecules, and you will get the corresponding states depending on the how much thermal excitation you have given to the molecule. So we know that cohesive force is maximum in a solid and almost negligible in the gas. That's why solid has a definite shape, correct? So what about a gas? Gas does not have a definite shape, and in this chapter we are going to study about kinetic theory of gases. So we are interested about this gases. So there are many scientists who dedicated their life in order to study this topic, the kinetic theory of gases. And in this chapter we'll be continuing lots of the topics. So broadly speaking, this kinetic theory of gases is based on basically two main postulates. One is matter is made up of identical particle, made up of identical particle or molecule. Then second postulate is thermal energy can be identified with the molecular motion. So thermal energy can be identified with molecular motion. So I will take a chance and explain you few concept here. So I will ask you a simple question. So imagine I have a solid which is made up of a metal. Okay, so a metal block, and there is a weighing scale. So I have a weighing scale and on this weighing scale I can place the object and it will show me how much kg it is. So how much is the mass of the sample. So imagine I have a metal block and I have a weighing scale, and so I'll take this object and place on the weighing scale. Okay, so and note the weight of that box. So now if it is showing me 5 kg, so imagine if it is showing me 5 gram. So next what I'll do is, so I'll take a Bunsen burner. So I'll take a Bunsen burner and I'll take this same 5 kg mass object and place it under the flame. 1 second. So I'll take the metal block and I'll place it under the flame. Okay, so after placing over the flame, imagine for 2 minutes, then I will pick it and keep it on the block. So now my question is, will the keep it on the weighing table. So my question is, will the mass be the same? So now initial mass was 5 gram. So what about the final mass? Will it be the same? So if your answer is yes, it will be the same, then your answer is wrong. But in this case, we see that there is a slight increase in the mass. Okay, so what is the conclusion here? So here when we observe this metal block, it is made up of atoms, correct? So when you don't supply any heat, so there is no energy supplied to this particles, correct? So when you apply the heat, the molecule will start to vibrate and there will be some additional energy added to the atoms. So this additional energy is causing the increase in the mass. So it won't be the 5 gram, so it might increase 5.03 gram. So somewhat like this it can increase. So this additional energy is converted into mass. So whenever you are referring to a mass, so we are referring to the energy that at atomic system, so the system of the atoms consist. And it is given also given by the famous E is equal to mc square equation, correct? So mass and energy are equivalent. But here let's not try to deviate on this matter, but what I'm trying to say is, so whenever you heat a new object, so there will be a thermal energy supplied to it and it causes the molecule to vibrate, and vibrate means there will be some thermal motion, okay, motion of the atoms. So what we can conclude is, so what I can conclude here is thermal energy can be identified with the molecular motion. So this was about the solid. So what about the gas? So if I'm going to apply the same principle for gas, so initially when you don't supply heat to the gas, the gas will be moving randomly with some velocity, correct? So now if I supply the flame or heat, now what happens? It will start to move more violently than before. So this will happen. So now this was about the introduction to kinetic theory of gases. So now whenever people started to study this subject, we don't know exactly how does a gas molecule react with the external temperature, pressure or anything. Okay, so basically what we do is we start to study from a simplest model available, then we go on increasing its complexities. So now let us start with the first topic of this chapter, which is basic assumption of kinetic theory. Kinetic theory. So we are going to oversimplify this model in the beginning stage. Then we are going to increase the complexities. Okay. So the first postulate in this kinetic theory is a gas consists of very large number of identical molecule. A gas consists a very large number of identical molecules. So if I consider a gas, okay, so I'm taking a is very ideal situation. So imagine this is a gas of helium atom. Okay, so here one helium atom, another helium atom, another helium atom. So I'm taking very ideal case. So if you look at our atmosphere, there is oxygen, nitrogen, there are many gases, carbon dioxide, so on in the atmosphere. So I'm taking is very ideal, very general case, like I'm considering only gases consisting of helium atom. So this is a first simplification what we do. So a gas consists of very large number of identical molecules. So here in this case I have taken identical helium molecules or particles. So now what do I mean by large number? What should be the ideal number? So usually this large number, what do I mean by large number is they should be the particle of gas comparable to the Avogadro number. And you know what is Avogadro number? So 6.022 into 10 to the power 23 atoms. So atoms per mole. So you have to have these many numbers of gas molecule. So in order to satisfy this assumption, yeah, in order to study the kinetic theory, the first condition is you have to have very huge number of gas molecules. What do I mean by huge large number means at least you have to have Avogadro number times the number of atoms. So you should have at least 6.022 into 10 to the power 23 number of atoms in order to apply the uh, kinetic theory of gases. Okay, so and if you look at the experimental evidence, we know that uh, if you take a space of 1 centimeter cube, so if I take a space of 1 centimeter cube, so imagine this is 1 centimeter cube space, so this will have at most 3 into 10 to the power 19 molecules. So only this, if you imagine very 1 centimeter, you know what is 1 centimeter, this much of length. So this much of length, if you construct a cube, it can fit up to 3 into 10 to the power 19 molecules. So it's a huge number. Okay, and this assumption is also valid. So that is our first assumption. The second assumption what we are going to take is the gas molecules can be regarded as point masses. Gas molecules are point masses. Point masses. So what do I mean by this? Okay, so we are taking, so if I am representing an atom, okay, hypothetically, even we don't know how atom look like. So if I consider a helium atom, so what I'm trying to say by this point is the radius of it should be very small. So this radius should be very small, very small, so that this whole sphere whatever I'm seeing should it should reduce to a point. Okay, so sphere whatever referring should reduce to a point, so that much small the particle should be. And whatever experiments that shows that uh, diameter of the gas molecule so are about 2 to 3 into 10 to the power minus 10 meter. So that's why this assumption is also valid assumption. Okay, so that's about the second postulate. And the third postulate of kinetic theory of gases, the gas molecules are in the state of constant random motion. So gases are in constant random motion. Okay, so if I'm considering a gas molecule, so one molecule is in this, moving in this direction, another is in this direction, another is in this direction, this one is in this direction, this one is in this direction. So if I consider such similar particles, so what you can observe here is these gases are moving in random direction, correct? So you can see the randomness here, randomness here. So why this is important? Because what we are saying is there is no preferential direction for this gas. These gases are not flowing in a single direction, correct? There is no change in mass here. So if I consider a condition, so the particles going out of the box, then there is a preferred motion of direction, right? So here we cannot apply the kinetic theory of gases. So here the gases are outflowing. So but in order to apply the kinetic theory of gases, what you have to consider is there should not be any motion of the preferential direction of the motion of the gas molecules. Okay, then only we can do the studies. So here the assumption is gases are in constant random motion. Okay, so another thing, another important assumption what we are going to apply while studying kinetic theory of gases is in absence of external field. So if I am not applying any external field or external force, the masses are distributed uniformly. In absence of external field, so this field can be any field. So here let's consider it to be a force field. In absence of external field, molecules are distributed uniformly. So if you are not applying any external force on the gas, okay, if there is no external field, so what happens is there would not be any preferential direction of a movement of gas molecules. So what happens, the gas molecule will be distributed uniformly throughout the container, right? Then we can apply our kinetic theory of gases. So what we are trying to do is, this is not a real case, so we are taking very ideal case. So what we are doing is we are very oversimplifying. First what we did, we considered large number identical molecule, correct? Second what we said, we will consider it to be point mass, we don't want to deal with the diameters and all. Then what we said is it's moving in random motion, so we don't want to include any preferential direction case. Then what we said, it is distributed uniformly throughout the container, correct? So we are trying to simplify as much as possible. Okay, so the fifth one is fifth assumption is the gas molecule experiences force only during collisions. So gas molecule experience force only during collision. So this is a consequence of the fourth postulate, correct? So if you are not applying any external field, so you're not supplying any force, correct? So the only force the gas molecule is going to experience is when it collides with each other. So when the gas molecule collide with each other, then only it will experience the force, correct? So when it collide with each other, or when it collides to the wall of the container. And to again simplify this, we will again try to simplify these assumptions, correct? So here from this assumption what we can say is there is no intermolecular forces. Okay, so there are no intermolecular forces of mutual attraction or repulsion between the molecules and the wall of container. That is, molecule of gas can be thought about moving freely, unaware of their presence of other molecules. In other words, what we can tell is the gases have only purely kinetic energy only. So that is the significance of this fifth postulate, right? So now again we'll try to simplify this. So the sixth assumption what we can say is the molecule of a gas behaves as rigid, perfectly elastic hard spheres. So the molecules behave like rigid, perfectly elastic hard sphere. So why this assumption? So now I said there will be some collision, right? So during the collision, so what can happen is there can be energy lost and there might be some deformation, correct? So now what we want to do is we want to try to simplify as much as possible, correct? So so what we'll say is first of all it is a rigid. So we'll say it is a rigid, then we'll say perfectly elastic. Even if there is any deformation formed, it will regain its original diameter. So it's a perfectly elastic. So there won't be any loss of energy or gain of energy during the collision. So momentum will be conserved and energy will also be conserved. So it means the molecule will neither lose the energy nor deform when they collide among themselves and the wall of the container. Okay, so that is the sixth postulate what we are going to assume. The seventh simplification what we are going to do is, so this tells about the duration of the collision is negligible compared to the time interval between successive collision. So as I said you, so let's write that statement. The duration of collision, the duration of collision is negligible compared to time interval between successive collision, compared to time interval between successive collision. So here in this assumption what we are going to say is, so you know the gas molecule will collide, okay, yeah, that's there. And by this specific assumption what do I mean is, so when the gas molecule will collide, correct, so the time of contact between those two, so the duration of collision, it is very less compared to the time interval between the successive collision, correct? So it might come into contact with the other molecule just for few millisecond or microsecond, but while traveling to other atom it might take a longer duration. So time interval between successive collision is more than the time duration of the collision. So that's the meaning of this. postulate. Okay, so the next postulate is all the molecules do not move with the same speed. So all the molecule do not move with same speed. So if you observe the gas molecule, so this might be moving with a higher velocity, this might be moving with a lower velocity, this might be moving with slightly higher velocity, correct? So this might be moving with same velocity but in opposite direction, correct? So these might be the different case, correct? So all the molecules may not move with the same speed or velocity. Okay, so that means there is a spread of molecular speed in a range, correct? So next one is the last postulate what we are going to observe here is the gravitational potential energy. So gravitational forces do not affect the motion of gases. The motion of gases. So it is very negligible, even though if there is a gravitational force between any two matter in this universe, but the forces are very negligible, so we can ignore it. So these are the few assumption, very simplified assumption, which we are going to assume in this chapter. So based on these assumptions, we study this whole kinetic theory of gases. So this is for today. So we'll start with the next topic in our next lecture. So thank you.